Hello and welcome. In this video, we're going to take a look at how we model variation. If you think about it, maybe a lot of the equations that we use on a common basis have come from some sort of scientific experiment, where we've taken measurements of one quantity and compared it to measurements of another quantity. And then we found some sort of relationship between those two quantities. That's what we mean between variation of the variables. We have one variable influencing another through some sort of relationship. Now, there's a couple different ways that we could express those relationships and then turn them into mathematical models. So let's start off with a direct model, a direct variation. In direct variation, let's suppose we have two quantities. We have some sort of quantity y and we have some sort of quantity x. And maybe in a scientific experiment, what we've done is we've taken the quantity x and we have increased it. And then we measured what happens to y as x increases. Now suppose that we've measured that y is also increasing. Y is increasing whenever x is increasing, and in the opposite direction, whenever x is decreasing, we see that y is also decreasing. This would be a direct variation, and we would say that y varies directly as x. Now, that's not to say that when x is increased by 2, that y is also directly increased by 2. We would say that as x increases, y increases proportionally, not necessarily by the exact same amount. Whenever the quantities are proportional, we could say that the ratio of y compared to x is some constant. Let's call that constant k. So k is the constant of proportionality. Now we like to rearrange this equation so that whatever we have for a value of x, we can plug in directly and compute the value of y. So we turn this model into y equals k times x. And this is our model for direct variation. Now, just a note here, k is not equal to 0. If k was equal to 0, then we'd always have y equal to 0, and we would have no relationship at all. Now see if you can think of any kind of examples of where we have direct variation. One example that we could think of is if we have an electric circuit with a resistor. We can measure the current flowing through this resistor, and we can measure the voltage. And we can do both of these things with some measurements. And suppose we gradually increase the current going through the circuit and measure the voltage. We might find that the voltage is directly related to the current. And we would say that the voltage is varying directly with current. Now, in this experiment, we have a k, which is our constant of proportionality. And that k might have some meaning. In fact, if you are familiar with some physics, this is actually Ohm's law, where k is the resistance of the resistor. K is equal to some constant R, where R would be the resistance. Now, how would we use this formula? Now that we've set up some sort of model, maybe we would understand that if we just plug in a value for current and find out what the voltage is, we can actually come up with a value for the constant of proportionality. So let's suppose when the current going through this is 2 amps, that we find that the voltage is 1000 volts. Well, plugging those values in, we can decide for ourselves what that constant proportionality must be. In this case, we would have 1000 equals k times 2. Solving for k, we see that k is going to be equal to 500. Now we can also use the units of I and V to find out what the units of k must be. So we have units of 1000 volts divided by units of 2 amps. So this would be 500 volts divided by amps. Now, as it turns out, we've already created a new unit for volts divided by amps, and you may need to know a little bit about the application here with electronics to understand that, but we call the units here ohms. Resistance is actually measured in ohms, which has the omega symbol. But now that we've got the model, we can see that voltage is just always going to be equal to 500 times I. And then this model here will allow us to change current to any value that we like, plug it in, and find out what the voltage is. So here's an example where we have direct variation, but then we sometimes will find that y does not vary directly as x. It's quite possible that sometimes when we increase the value of x, we'll see that y decreases. Let's take a look at that kind of example. With inverse variation, we will see that when x is increasing, y decreases. Now we can come up with another model that's similar. It'll have a constant of proportionality, and if we wish to find y, we can see that y is going to equal some sort of constant of proportionality times the reciprocal of x, 1 over x. And if you take a look at this, as x gets larger, k continues to get divided by a larger and larger value. But since k is a constant, we have a numerator that stays exactly the same, divided by a much larger number. So that will eventually get smaller, and y decreases. So we can write this as k times 1 over x, or we can simply say y equals k over x. We would say that y varies inversely as x. One example of an inverse variation, if you think about musical instruments, especially thinking about a stringed instrument. If we have a string on an instrument that is a particular width, a particular thickness, as we start to increase its length, the length is increasing, but the frequency ends up decreasing. We hear a deeper pitch for a longer string. So we have some sort of model, let's say as an example, where we have frequency. For frequency, we'll use f, and we'll say that it inversely is proportional to the length of the string. Now, of course, we're taking out any other variables that might have to do with strings, and we're just looking at simply the length of a string. And we would say, since f varies inversely with respect to length, that f is equal to some constant proportionality divided by L. And if we are given a length of string and a frequency for that length, then we can find out what k is. We can also decide what the units of k are by looking at the units of frequency and length. Once we know what k is, then we have a complete model, and we can determine a frequency for any given length of a particular string. Now, it's quite possible that there's more than one variable. Frequency, for instance, isn't just dependent on the length, it's also dependent on the tension of the string, it's also dependent on the thickness of the string. So, when we start getting combinations of multiple relationships, then we have a little bit more confusing wording, but we can still always have a constant proportionality. If we say that A is a quantity that is jointly proportional to quantity B and quantity C, then we could say that A is equal to some constant of proportionality times B times C. So we can see two variables here that are directly having a relationship on A. As B or C increases, so does A. And as B or C decreases, so does A. And this would be called a jointly proportional relationship. Now, we may not always have something that is linear with respect to each individual variable. It's quite possible that we'll have a quantity be directly proportional or inversely proportional to some operation on the other variable. Let's look at another example. If we say that y is inversely proportional to the square of x, then first we should take a look at the word inversely proportional. So we know that y is going to be inversely proportional to something when we have k over that something. But in this case, it's not inversely proportional to x. It's inversely proportional to the square of x. So that would mean it is k over x squared. And once again, there's only one constant of proportionality. If we are given a value of x and a value of y associated with it, we can find out what k is and complete the model. None of these models are totally complete unless we actually know what k is in our particular example. Now, what if we have something that is both directly proportional and inversely proportional to various quantities? We could put them all together. Here we can say that r is directly proportional to s and inversely proportional to the square root of t. So since r is proportional to the other quantities, r can be put to the one side of the equation. We've got a constant of proportionality, which we could use k. And really, we can use k in just about any circumstance, except when k is also going to be one of the other quantities. It is directly proportional to s, so k times s, inversely proportional to the square root of t. So root t ends up in the denominator. Now, a classic example where we have several quantities all directly related is we could take a look at the force of gravity between two masses. The gravitational force between two objects is jointly proportional to their masses and inversely proportional to the square of the distance between them. So, we'll try to think of some useful letters to represent these quantities, and the first quantity is gravitational force. Force we could have as a capital F. And now if you really want to, if you're already aware that there's more than one type of force, we would maybe use a little subscript, Fg, if you wish. Then it's more obvious that this force is a particular type of force. Now, it is jointly proportional to their masses, so we'll leave room for some sort of constant of proportionality. And since we have two masses, maybe we'll let one be m1, and we'll let the other mass be m2, and we can use these little subscripts so that they are different, unique values. And inversely proportional, so we know we have some sort of fraction, the square of the distance between them. And you could use d for distance, but we often, in this sort of application, think about a radius. And so we'll use r. And it's the square of that distance, r squared. Now, this might be one of the opportunities for you to use a letter other than k. If you've seen this equation before, this constant of proportionality is a gravitational constant, so sometimes we use a capital G there. Once again, this is another model that can be obtained through some experimentation, keeping as many variables as possible constant and varying one at a time. And once we have varied each individual variable, then we can come up with a model that puts all of the quantities together and forms a relationship. So I hope that's kind of given you a little bit of an idea about how we come up with mathematical models. Most of the time we need to obtain some data first through some sort of experimentation, and then we use these terms such as inversely proportional or inversely related, directly proportional or directly related, and anytime that we see that something is proportional, we need a constant of proportionality. We can't just slap an equal sign that force is equal to distance, especially because they don't even have the same units. Force and distance measure different things. That constant in there is so that we can come up with a way to explain the relationship, and the constant also has some sort of units attached to it that can come from the problem that help explain the whole thing. So I hope that gives you a little bit of insight. It's a great way to find out where some of the equations that you're familiar with already come from. Thanks for watching, and I'll see you in the next video.